Hi, welcome to Google Open Source Live. My name is Ian Lance Taylor. This talk is pre-recorded, so I'm speaking to you from the past. My present self will be watching the chat down there, so feel free to ask questions. We'll be talking about when to use generics, which is a new language feature that won't be available until the future. Generics will be available in the Go 1.18 release in February 2022. To start with, what are generics? Generics let you write data structures and functions with types that are specified later. In current Go, functions have parameters, of course. With generics, functions can have a new kind of parameters called type parameters. And types, which currently can't have any kind of parameters, can also have type parameters. Functions and types with type parameters can then be instantiated with type arguments. For type parameters, we say instantiated rather than called because the operation occurs entirely at compile time, not at runtime. Type parameters have constraints that restrict the set of permitted type arguments, much as ordinary parameters have a type that restricts the set of permitted ordinary arguments. For example, consider this function that takes a map and returns a slice containing all the keys in the map. In current Go, it's easy to write this function for any specific map type. This example works for maps of type map string int, but you need to write a different copy of the function for each map type that you want to use. Or you could write this function using the reflect package, but that is awkward to write and relatively slow to run. Using the reflect package here is complicated enough that I won't show an example. Or you could use type parameters. With type parameters, you can write this function once in a way that will work for all map types and will be fully type checked by the compiler. Here the type parameters are named k and v. The ordinary parameter m, which used to have type map string int, now has type map kv. The type parameter k is the key type of the map, so it has to be comparable. This is expressed by saying that the constraint for k, which again you can think of as the meta type for the type parameter, is the pre-declared constraint comparable. The type parameter v can be any type, so its constraint is the pre-declared constraint any, which permits any type. The body of the function is just like before, except the variable s is now type slice of k rather than type slice of string. There are a lot more details of these new language features that I'm not going to discuss here. The important point is that functions can have type parameters, and although this example doesn't show it, so can types. The link on the screen shows you where you can read a lot more about this. What I'm going to talk about today is not what generics are or how to use them, but rather when to use generics and when not to use them. To be clear, this talk will provide general guidelines, not hard and fast rules. Use your own judgment, but if you aren't sure, use the guidelines I'm going to discuss now. Let's start with a general guideline for programming in Go. Write Go programs by writing code, not by defining types. When it comes to generics, if you start writing your program by defining your type parameter constraints, you're probably on the wrong path. Start by writing functions. It's easy to add type parameters later when it's clear that they will be useful. That said, let's look at those cases where they can be useful. One case where type parameters can be useful when writing functions that operate on the special types that are defined by the language: slices, maps, and channels. If a function has parameters with those types, and the function code doesn't make any particular assumptions about the element types, then it may be useful to use a type parameter. For example, the map keys function that we saw earlier. That function returned a slice of all the keys in a map. The code didn't assume anything about the map key type. That made it a good candidate for using type parameters. As I mentioned before, the alternative to using type parameters for this kind of function is typically to use reflection. But that's a more awkward programming model, it's not statically type checked, and it's often slower as well. Another similar case where type parameters can be useful is for general purpose data structures. By general purpose data structures, I mean a data structure like a slice or a map, but one that's not built into the language. For example, a linked list or a binary tree. Today, programs that need such data structures write them with a specific element type, or they use an interface type. Replacing a specific element type with a type parameter can produce a more general data structure that can be used in other parts of the program. Replacing an interface type with a type parameter can often permit the data to be stored more efficiently as well. In some cases, using a type parameter instead of an interface type can mean that the code can avoid type assertions and can instead be fully type checked at compile time. For example, here's what a binary tree data structure might look like using type parameters. This is an example of a type that has a type parameter. Each leaf node in the tree contains a value of the type parameter t. When the tree is instantiated with a particular type argument, values of that type argument will be stored directly in the leaf nodes. They will not be stored as interface types. And this shows the method on the generic binary tree. Don't worry about the details here or the formatting used to fit the code onto the slide. The point is that this is a reasonable use of type parameters because the tree data structure and even the code in this method is largely independent of the element type t. The data structure does need to know how to compare values of element type t, and it uses a passed-in comparison function to do that. You can see that on the fourth line in the code here, in the call to bt.comp. Other than that, the type parameter doesn't matter at all. This binary tree example illustrates another general guideline. When you need something like a comparison function, prefer using a function rather than a method. We could have defined the tree type such that the element type is required to have a compare or perhaps a less method. This would be done by writing a constraint that requires a compare or less method, and it would mean that any type argument used to instantiate the tree type would need to have that method. But that would mean that anybody who wants to use tree with a simple data type, like int, would have to define their own int type with a compare method. And anybody who wants to use tree with a custom data type would also have to define a compare method for their data type, even if it's not otherwise needed. If we define tree to take a function, as we did in the example code that we just saw, then it's easy to pass in the desired comparison function. And if the element happens to already have a compare method, we can simply pass a method expression like elementtype.compare as the comparison function. To put it another way, it's much simpler to turn a method into a function than it is to add a method to a type. So for general purpose data types, prefer a function rather than writing a constraint that requires a method. Another case where type parameters can be useful is when different types need to implement some common method and the implementation for the different types all looks the same. For example, consider the standard library's sort.interface from the sort package. It requires that a type implement three methods, len, swap, and less. This example shows slicefun, a generic type that implements sort.interface for any slice type. For any slice type, the len and swap methods are exactly the same. The less method requires a comparison, which is the fun part of the name slicefun. As with the earlier tree example, we will pass in a function when we create a slicefun. This code shows how slicefun is used to sort any slice using a comparison function. Here, we use type parameters to implement the sort.interface methods for any slice type. Using type parameters is appropriate for this example because the methods look exactly the same for all slice types. I should mention now that Go 118 will most likely include a generic function to sort a slice using a comparison function, and that generic function will most likely not use sort.interface. But the general point is still true, even if this specific example will most likely not be useful in the future. It's reasonable to use type parameters when you need to implement methods that look the same for all the relevant types. Now let's talk about the other side of the question, when not to use generics. When are type parameters not a good idea? Well, Go has interface types. Interface types permit a kind of generic programming already. For example, the widely used io.reader interface provides a general mechanism for reading data from any value that contains information, such as a file, or that produces information, such as a random number generator. If all you need to do with a value of some type is call a method on that value, use an interface type rather than a type parameter. io.reader is easy to read, it's efficient, and it's effective. There's no need to use a type parameter to read data from a value by calling the read method. For example, do not write code like this. This same function could be written without the type parameter. Omitting the type parameter will make the function easier to write, easier to read, and the execution time will likely be the same. It's worth stressing that last point. People familiar with C++ in particular may assume that a function instantiated with a specific type argument will tend to be slightly faster than similar code that uses virtual methods. I said virtual methods because that's what C++ uses. What C++ calls virtual methods is, for purposes of this talk, similar to what Go calls interface methods. In Go, while of course the exact details are going to depend on the compiler, a function instantiated with a type argument will most likely not be faster than similar code that uses interface methods. So don't use type parameters for reasons of efficiency. Use them because they make your code clearer, and avoid them when they make your code more complicated. Going back to the choice between type parameters and interface types, when there's a common method that is used by different types, consider the implementation of that method. Earlier, we said that if the implementation of the method is the same for all types, use a type parameter. Inversely, if the implementation is different for each type, then use different methods. Don't use a type parameter. For example, the implementation of read from a file is nothing like the implementation of read from a random number generator. That means that we write two different read methods, and neither method should use a type parameter. Although I've only mentioned it a couple of times today, Go also has reflection. Reflection does permit a kind of generic programming in that it permits you to write code that works with any type. If some operation has to support even types that don't have methods, so interface types don't help, and if the operation is different for each type, use reflection. An example of this is the encoding JSON package. We don't want to require every type that we encode to support a Marshall JSON method, so we can't use interface types. But encoding an integer type is nothing like encoding a struct type, so we shouldn't use type parameters. Instead, the package uses reflection. The code is too complicated to show here, but take a look at the package source code if you're interested. In closing, this whole discussion can be reduced to one simple guideline. If you find yourself writing the exact same code multiple times, where the only difference between the copies is that the code uses different types, consider whether you can use a type parameter. Another way to say this is you should avoid using type parameters until you notice that you're about to write the exact same code multiple times. Thanks for listening, and I hope you will all use generics in Go when they're available, wisely and well. Thank you.